Have you ever wondered if we are alone in the universe? Are there other intelligent civilizations out there, waiting to be discovered? Or are we the only ones who have reached this level of technological and cultural development? How likely is it that we will ever encounter an extraterrestrial being, either in our own solar system or beyond? Hello and welcome to Curiosity, where we explore fascinating and interesting topics about everything. Today's topic is, what are the chances of meeting an alien? These are some of the questions that have intrigued scientists, philosophers, and ordinary people for centuries. The search for alien life is one of the most exciting and challenging endeavors of our time. It involves not only astronomy and physics, but also biology, chemistry, psychology, sociology, and ethics. It requires us to expand our imagination and our understanding of what life is and how it can evolve. In this episode, we will explore some of the latest discoveries and theories about exoplanets, the planets that orbit other stars than our Sun. We will also look at some of the methods and technologies that are used to detect and study these distant worlds. And we will discuss some of the implications and possibilities of finding life beyond Earth. Let's start with some basic facts. According to NASA's Exoplanet Archive, as of September 1, 2023, there are 5,506 confirmed exoplanets in 4,065 planetary systems, with 878 systems having more than one planet. These numbers are constantly increasing as new observations and analyses are made by various telescopes and missions. The first confirmed detection of an exoplanet occurred in 1992, when two planets were found orbiting a pulsar, a rapidly spinning remnant of a massive star that exploded as a supernova. The first confirmed detection of an exoplanet around a normal star happened in 1995, when a giant planet, 51 Pegasi b, was discovered orbiting 51 Pegasi, a star about 50 light-years away from Earth. Since then, many different methods have been developed and improved to find and characterize exoplanets. Some of the most common ones are as follows. Transit photometry. This method measures the slight dimming of a star's brightness when a planet passes. This allows us to estimate the size and orbital period of the planet, as well as some information about its atmosphere if it has one. Doppler spectroscopy. This method measures the tiny shift in the wavelength of a star's light due to its motion caused by the gravitational pull of an orbiting planet. This allows us to estimate the mass and orbital shape of the planet, as well as some information about its composition if it has one. Direct imaging. This method involves taking pictures or spectra of a planet directly, by blocking out the glare of its host star using various techniques. This allows us to study the planet's physical appearance, temperature, weather, and chemistry. Each method has its advantages and limitations, depending on the type and distance of the star and planet involved. Sometimes, more than one method can be used to confirm and complement each other's results. For example, the Kepler Space Telescope, which was launched in 2009 and retired in 2018, used transit photometry to detect thousands of exoplanet candidates, many of which were later confirmed by other telescopes using Doppler spectroscopy or direct imaging. One of the main goals of exoplanet research is to find planets that are potentially habitable, meaning that they could support life as we know it. This usually involves looking for planets that are similar to Earth in size, composition, temperature, and distance from their star. However, this is not a simple task, as there are many factors that affect a planet's habitability, such as its atmosphere, magnetic field, rotation rate, moon presence, tidal forces, stellar activity, and cosmic radiation. One way to narrow down the search is to focus on the habitable zone, or sometimes called Goldilocks zone, which is the range of distances from a star where liquid water can exist on the surface of a planet. Liquid water is considered a key ingredient for life as we know it, because it is essential for many biochemical reactions and processes. However, the habitable zone is not a fixed or universal concept. It depends on the type and age of the star, as well as on the properties and feedbacks of the planet itself. For example, according to one study, about 1 in 5 Sun-like stars have an Earth-sized planet in their habitable zone. However, this does not mean that all these planets are actually habitable or inhabited. They may have different atmospheres or histories that make them unsuitable for life. On the other hand, some planets that are outside the conventional habitable zone may still be habitable or inhabited. They may have alternative sources of heat or energy that allow them to maintain liquid water under certain conditions. For instance, some moons of Jupiter and Saturn, such as Europa and Enceladus, are thought to have subsurface oceans of liquid water heated by tidal forces from their giant planets. Another way to narrow down the search is to look for biosignatures, which are indicators of biological activity on a planet. These could be chemical, physical, or spectral features that are produced or influenced by living organisms. For example, some gases in a planet's atmosphere, such as oxygen, methane, or nitrous oxide, could be signs of photosynthesis, respiration, or metabolism by certain types of life forms. However, biosignatures are not definitive proof of life. They could also be produced by non-biological processes, such as volcanism, lightning, or cometary impacts. Therefore, biosignatures need to be interpreted carefully and in context with other information about the planet and its environment. One of the most ambitious and promising missions that will search for habitable planets and biosignatures is the James Webb Space Telescope. JWST is a joint project of NASA, ESA, and CSA, and it will be the successor of the Hubble Space Telescope. JWST has a 6.5-meter primary mirror and 4 scientific instruments that will operate in the infrared range of the electromagnetic spectrum. This will allow JWST to observe fainter and cooler objects than Hubble, such as distant galaxies, brown dwarfs, and exoplanets. JWST will use a combination of transit photometry and direct imaging to detect and study exoplanets. It will also use spectroscopy to analyze the light from exoplanets and their atmospheres, looking for clues about their temperature, composition, chemistry, and biosignatures. JWST will be able to observe hundreds of exoplanets, including some that were previously discovered by other telescopes, as well as some that are yet to be discovered. Some of the main targets for JWST will be as follows. TRAPPIST-1. This is a system of 7 Earth-sized planets orbiting a red dwarf star about 40 light-years away from Earth. 3 of these planets are located in the habitable zone of their star, and they may have liquid water on their surfaces. JWST will try to determine if any of these planets have atmospheres, and if so, what they are made of and how they affect the climate and habitability of the planets. Proxima Centauri b. This is a planet about 1.3 times the size of Earth, orbiting a red dwarf star about 4.2 light-years away from Earth. This is the closest exoplanet to our solar system, and it is also located in the habitable zone of its star. However, its star is very active and emits strong flares and winds that could erode or strip away the planet's atmosphere. JWST will try to detect if this planet has an atmosphere, and if so, how it protects the planet from its star's radiation. Kepler 186f. This is a planet about 1.1 times the size of Earth, orbiting a red dwarf star about 500 light-years away from Earth. This is the first Earth-sized planet discovered in the habitable zone of another star. However, its star is much dimmer than our Sun, so the planet receives much less light and heat than Earth does. JWST will try to measure the temperature and albedo of this planet, as well as any possible signs of clouds or vegetation. These are just some examples of the exciting and diverse worlds that JWST will explore in its quest for finding life beyond Earth. Of course, there are many more exoplanets that await discovery and investigation by JWST and other telescopes in the future. The field of exoplanet research is constantly evolving and expanding, as new data and theories emerge. So what are the chances of meeting an alien? The answer is, we don't know yet. But we are getting closer to finding out. The search for alien life is not only a scientific endeavor, it is also a philosophical and existential one. It challenges us to rethink our place in the universe and our relationship with other forms of life. It inspires us to wonder about the origin, diversity, evolution, and destiny of life in general. That's all for today's episode. Thank you for watching Curiosity. If you enjoyed this video, please like and subscribe for more content like this. And don't forget to share your thoughts and questions in the comments below. Until next time, stay curious.